In this video, I'm going to be looking at several example problems looking at projectile motion where objects are thrown horizontally. These are sometimes referred to as zero launch angle problems because they're only moving in the horizontal direction initially. Their angle that they make with the horizontal is 0 degrees. So that means that there's only going to be a horizontal component to the initial velocity, and the vertical component of the initial velocity is going to be 0. In this first problem, we have a helicopter that's flying horizontally at a speed of 60 meters per second. And it's a height of 300 meters off the ground. When it releases a bomb that's unarmed, so it accidentally releases a dummy bomb, and we're trying to figure out where that bomb hits the ground. So when something is dropped, the initial velocity of the object is the same as the velocity that it had right before it's dropped. So the velocity right after it's dropped is the same as right before it's dropped. This is a property based on its inertia. An object with inertia will stay in motion until a force acts on it to change its motion. So if it's moving at 60 meters per second horizontally, right after it's dropped, there hasn't been time for anything to change its velocity, and so it's still moving at 60 meters per second horizontally right at that point. So this is going to go and it's going to strike the ground at some distance away. When you're looking at projectile motion problems, which are examples of two-dimensional motion with a constant acceleration, we solve them similar to one-dimensional problems. One of the ways to do that is to set up a table of data looking at the horizontal initial position, final position, initial horizontal velocity, final horizontal velocity, horizontal acceleration, and the time. And so for this, I'm going to let it start at a horizontal position of 0 because I'm trying to find how far from that starting horizontal position does it land. It's moving at 60 meters per second horizontally at the beginning, and the horizontal acceleration is 0. There's nothing pushing or pulling on it horizontally to give it a horizontal acceleration. But in these two-dimensional problems, we also have to do the exact same thing for the vertical direction. And when we're setting up this vertical column, we're only looking at vertical quantities. The positions are the vertical positions, or the heights of the object. The velocities are only the vertical components of the velocity. The acceleration is only the vertical component of the acceleration. And so this helicopter is starting at a height of 300 meters. It's not moving up or down at all. So the bomb is not moving up or down at all at the beginning. So the initial vertical velocity is 0. That's one of the key things that people leave out. They see the 60 meters per second and they want to plug in 60 meters per second for both initial velocities. That 60 meters per second is only in the x direction, which means that there's no y component to that initial velocity. The vertical acceleration is negative 9.8. And what we're doing in part A is we're finding at what time is the object at the ground. At what time is the height of the object 0? So to do that, we're going to look at the vertical motion. And we're going to use the equation for the vertical position as a function of time. The final height equals the initial height plus the initial vertical velocity times the time plus 1/2 times the vertical acceleration times the time squared. Again, in this equation, if we're looking at the vertical motion, we only look at the vertical quantities, the vertical starting position, the vertical initial velocity, the vertical acceleration. We don't plug in any horizontal values. And so looking back at our table, the starting height is 300 meters, the ending height is 0. So we have 0 equals 300 meters plus 0 meters per second times t, and 0 times anything is 0, plus 1/2 times negative 9.8 meters per second squared times t squared. So we're going to solve this equation for t. So we have 0 equals 300 minus 4.9 t squared. So half times negative 9.8 is negative 4.9. So we get that t squared is 300 divided by 4.9. Or I take the square root of both sides, and I get that the time is 7.8246 seconds. So the time that it takes for this bomb to reach the ground is 7.8246 seconds. So now I can fill in that time in my data table if I'd like. So this is 7.8246 seconds. So then in part B, we're trying to find how far it travels horizontally. We're looking for this horizontal distance. But what we're actually doing is we're trying to find what is the horizontal position at the time 7.8246 seconds. That's the time when it was at the ground. So to do that, we're looking at the horizontal motion. We're going to look at the horizontal motion as a function of time. And that equation is x equals the starting position, x0, plus the initial horizontal velocity times the time, plus 1/2 times the horizontal acceleration times the time squared. And if we look back at our table, this horizontal acceleration is 0. So this last term is 0. I'm going to fill in 0 right away so that I don't forget to do it. A common mistake that people will make is they'll plug in the vertical acceleration of negative 9.8 meters per second squared when they're looking at the horizontal motion. You only look at the horizontal quantities when you're looking at the horizontal motion. So I have that this position x equals the starting position of 0 meters plus the initial horizontal velocity, which was 60 meters per second, times 7.8246 seconds. Again, those were the numbers from the table, so I had this initial velocity and this time, and I was looking for the final horizontal position. And so doing that, I get that the final horizontal position is 469.476 meters. And then the third question is asking for the horizontal and vertical components of the bomb's velocity just before it strikes the ground. Again, sometimes people are tempted to say, oh, it hits the ground so the velocities are 0. But that's not what we're looking for. Once it strikes the ground, this is not a projectile motion problem anymore. So we're looking at the projectile motion part, which is from right after it's dropped until right before it strikes the ground. And so we need to find the x and y components of the velocity at a time of 7.8246 seconds. In the horizontal direction, because there's no acceleration, the horizontal velocity stays 60 meters per second. If it was 60 meters per second at the beginning, it stays 60 meters per second. That's what 0 acceleration in the horizontal direction means. The horizontal velocity does not change. But to find the vertical velocity, we do have something that's accelerating. So that vertical component of the velocity we find by looking at the equation that relates velocity and time. So we have this unknown vertical velocity, Vy, equals the initial vertical velocity of 0 meters per second plus negative 9.8 meters per second squared times 7.8246 seconds, which gives a vertical velocity of negative 76.681 meters per second. So the negative sign means that it's moving downwards. So right before it reaches the ground, that bomb is moving downwards. So we just used our quantities that we had from our vertical column. We knew the initial vertical velocity, we knew the vertical acceleration, we knew the time. We were looking for that final vertical velocity. If the question asked you to go a step farther and find the magnitude and direction of the velocity right before it reached the ground, you would just take those components and combine them together. You would have an x component of 60 meters per second. You have a y component that's down, that's 76.681 meters per second. And so the magnitude of your velocity, which is also referred to as the speed of the object, the speed would be the square root of 60 squared plus 76.681 squared, which if you calculate that, that's 97.365 meters per second. So sometimes the question might say, what is the speed that it has right before it hits the ground? That speed would be 97.365 meters per second. The speed is the magnitude of the velocity. It's not the x component or the y component, it's the two put together. And then to get the direction, I would calculate the angle that the velocity vector makes with the horizontal. The tangent of that angle is the opposite side, 76.681, divided by the adjacent side of 60. So that angle would be the inverse tangent. Again, to undo the tangent function, I use the inverse tangent function. So it's the inverse tangent of 76.681 over 60, which would give me an angle of 51.958 degrees, and that angle is below the x-axis. So again, you can be asked things like the time to reach the ground, the horizontal distance traveled. You can be asked to find the x and y components of the velocity at some time during the motion. These are all common things to look at. In this next problem, we have a swimmer that's jumping off a cliff. And we want to figure out what velocity the swimmer needs to have to just clear this ledge. And so what we're going to do is we're going to look at what velocity she would have to reach the very edge of this ledge. And so that would be the minimum speed. So she would just skim the edge at that point. And then anything bigger than that, she would clear the ledge. So again, we're going to set up our horizontal column. So the initial horizontal position is 0. The final horizontal position is the edge of this ledge, which is 1.75 meters. The initial horizontal velocity, we don't know. That's what we're looking for here. This is only in the x direction. Again, with this, if she runs horizontally, this means that the initial vertical velocity is 0. Again, in these zero launch angle problems, where something is moving horizontally at the beginning, the initial vertical velocity will be 0. Again, the horizontal acceleration is 0 meters per second squared. Then in the vertical direction, the diver is starting at a height of 9 meters, and she's ending at a height of 0 meters. So I'm calling this ledge where the height is 0, and so she's starting 9 meters above 0. The initial vertical velocity, again, is 0 meters per second. The vertical acceleration is negative 9.8 meters per second squared. And so to find the horizontal velocity, we first have to calculate at what time she reaches the height of the ledge. At what time does she reach a height of 0? Because then we know that she traveled 1.75 meters in that time, and so we can find the horizontal velocity. So we're first going to look at the vertical motion to find the time. So we're going to use a similar equation that we used in the last problem, the height as a function of time. Again, looking at our values, we have that the final height, 0, equals the initial height of 9 meters plus 0 meters per second times t plus 1/2 times negative 9.8 times t squared. Again, if you look back at the problem that we just did, this is the exact same way that we found the time. Again, 0 times t is 0. So we have that 0 equals 9 minus 4.9 t squared, or t is the square root of 9 divided by 4.9, which is 1.355 seconds. Again, you add the 4.9 t squared to the other side, divide by 4.9, take the square root, you get 1.355 seconds. And now we know that she traveled 1.75 meters horizontally in that time. So we can use that to find the initial horizontal velocity. Again, we're going to use x equals the starting position plus the initial horizontal velocity times the time plus 0. Again, since the horizontal acceleration is 0, 1/2 ax times t squared is 0. So again, looking at the diagram, it starts at 0, it ends at 1.75 meters. So I have 1.75 meters equals 0 meters plus the unknown horizontal velocity v0x times the time of 1.355 seconds. So I can solve for that, and I get that her horizontal velocity is 1.75 over 1.355, which is 1.2913 meters per second. So again, if she jumps with a speed of 1.2913 meters per second, she is just going to skim the edge of the ledge. And so if she jumps with a speed that's bigger than that, she will make it over the edge. Okay. One last problem. I'm going to look at an arrow that's fired horizontally. So it's fired at an initial velocity in the horizontal direction of 40 meters per second. And it's fired directly towards the bullseye of a target. And that target is a horizontal distance of 20 meters away. But if it's fired at the target, when this goes, it's going to hit below the bullseye. And we're going to try and figure out how far below the bullseye does it hit. So again, in the horizontal direction, the starting horizontal position is 0. The ending horizontal position is 20 meters. The initial horizontal velocity is 40 meters per second. The horizontal acceleration is 0. In the vertical direction, I'm going to let the initial height be 0, so that my final height is how far down it hits. Again, if it's fired horizontally, this initial vertical velocity is 0 meters per second. The vertical acceleration is negative 9.8. And so this is one where I'm going to use the horizontal motion to find the time. If I know this starting position and this ending position and the starting velocity, that's what I'm going to use to find the time. If I look back at the other two problems, I knew the starting and ending heights and the initial vertical velocity, so I used the vertical motion to find the time. Here, I know the starting and ending horizontal positions, and the horizontal velocity, so I can use that to find the time. So I'm finding the time to reach the target, or the time that it takes to travel 20 meters horizontally. So my horizontal equation is the horizontal velocity times the time. Again, because there's no horizontal acceleration, that last term is 0. So I have that 20 meters equals 0 plus 40 meters per second times t plus 0. So that gives a time of 20 over 40, or 0.5 seconds. And so then I have to find how far does it fall in 0.5 seconds. So I know that this time is 0.5 seconds. I'm looking for this final height. So again, I'm going to use the vertical equation for position and time. And so I have this final height equals the initial height of 0 plus 0 meters per second times 0.5 seconds plus 1/2 negative 9.8 meters per second squared times 0.5 squared. Again, 0 times anything is 0. So I get this height is negative 4.9 times 0.5 squared, which is negative 1.225 meters, which means that it hits down 1.225 meters from its starting height. So again, these are kind of the three variations you get on zero launch angle problems. Sometimes you're told the starting and ending horizontal positions and the starting horizontal velocity, and you find the vertical distance. Sometimes you're given the starting and ending horizontal positions and the starting and ending vertical positions, and you find the initial velocity. Sometimes you're given the height and the initial horizontal velocity, and you find the horizontal distance. So these are all similar types of problems, but each one is a slightly different setup. These are all important types of problems to understand.